So this exercise related to particle physics and accelerators. We did this topic last week, and I will solve the MCQs from 34 onwards, like 35 onwards. Which of the following particles is a lepton? So if you want to work out the lepton, how we'll know which particle is a lepton? Lepton and quarks are the fundamental particles. So what is a muon? What are the leptons? Leptons are electron, electron neutrino, tau, tau neutrino, muon, muon neutrino. So muon is a lepton. What about neutron? Neutron is a baryon. Baryon means it's a combination of three quarks. When three quarks are together, we call that as a baryon. What about pion? Pion is a meson. Meson means it's a combination of quark and antiquark. Like combination of two quark in which one is quark, another one is antiquark. And what about the proton? Proton is also a baryon. So that's why A is the right answer for this. Question 36. A beam of electron is made to travel in a circular path by applying a magnetic field across the beam, across the path of the beam. Which of the following is the direction of a magnetic field to maintain a circular path? This is very important. Just you have to recall the Fleming's left-hand rule and the right-hand rule. So if it is a negative particle, we'll use our right hand. If it is a positive particle, we'll use our left hand. So in this case, it's a beam of electron. Electron means it's a negative. So it's a beam of electron. Which hand we'll use? We'll use our right hand. In a right hand, the first finger should represent the direction of a magnetic field. The second finger represent the direction of the particle, which direction the particle is moving. And the thumb will show the direction of the force. So we'll try to apply the rule and we'll figure it out which direction the magnetic field is pointing. So you will use your right hand, and in a right hand rule, all should be 90 degree. When you're using your right hand, all of them should be 90 degree to each other. Like, so you have So we want to work out, we have to use a right hand rule. So index finger is pointing the direction of a magnetic field. Second is representing the direction of the particle, and thumb is pointing in the direction of the force. So in this case, we know the force is pointing towards the left as the beam is moving. This is the direction of the force. So this is the direction in which the force is acting. So my thumb should point, as you can see, we are applying a right hand rule. So we are applying a right hand rule. The index finger is pointing. Index fingers represent the direction of magnetic field, which we don't know. And we have different options are there. Magnetic field is in, magnetic field is out, magnetic field to the left, magnetic field to the right. So if we try to figure it out, the beam of electron is moving downward. So my index finger should point downward. Sorry, my second finger should point downward. That's the direction of the particle. As you can see here, so the particle is moving in this way. So my second finger will point in the direction of the particle. My thumb will represent the direction of the force, which is towards the left-hand side. So my second finger is pointing in the direction of the particle. My thumb is pointing towards the force. So where my index finger is pointing, that is a magnetic field. So where my index finger is pointing, is it towards the screen or out of the screen? Into the page or out of the page? So it is pointing into the page. So that's why B will be the right answer. Is it clear how we worked out? When to use a left hand? If it was a positive particle, then we'll use a left hand. If it is a negative particle, if it's a positive particle or the conventional current, we take a left hand. But if it's a negative particle, we'll use the right hand. Yeah, same as the left hand, the right hand concept is the same. Only thing is the hand which we use, so the direction will change. The direction of a deflection will change as the particle changes. Next, we have a beam of electron is produced to investigate the wave properties of the particle. We know the wave particle duality, the particles can act like a can act like a particle. And according to the de Broglie's formula, that lambda is equals to h over mv or h over p. That's a relation between the wavelength, the Planck's constant, and the momentum. Which of the following would decrease the wavelength associated with electron? If electron was acting, electron is a particle, but if it was acting like a wave, then which of them will decrease? So if we want to decrease the wavelength, what we should do? If we want to decrease the wavelength, we should increase the momentum. And how we can increase the momentum? Momentum is a product of mass and velocity. So mass cannot be changed, but the velocity can be changed. Mass will change if it will move relative to speed of a light. Yes, the mass do change. But in this case, if it's not moving close to speed of light, the mass will not change. So applying a smaller potential, if we apply a smaller potential, the speed will be less because the less amount of electrical energy is supplied. So it will have a lower kinetic energy. So speed will be less. Decreasing a momentum, if we decrease the momentum, so it won't decrease the wavelength, it will increase the wavelength. Increasing a distance between the anode and the cathode. So if we increase the distance between the anode and the cathode, so as a result, the force which is experienced by because when two oppositely charged plates are having a closely space, then they will have a stronger electric field. Stronger electric field means stronger force is there. But if the same potential I increases the spacing between the plates, so the force on the charge decreases. If the force on the charge decreases, the speed or the acceleration will be lower or the final speed will be less. So increasing a velocity of electron, if you increase the velocity of electron, so its momentum will increase. And if the momentum will increase, the wavelength associated with this electron, that will be shorter. Is it clear, this one? So what we should do, we should increase the velocity of this electron. In question 36, accelerators are used to collide high energy particles so that their interaction can be studied. So what is the main purpose of the particle accelerator? So we can collide these particles at high speeds and we produce different particles because the energy can be converted into mass or mass can be converted into energy. So it will produce different smaller fragments. Which of the following quantities not always conserve in interaction between the particle? So in interaction between the particle, which of the quantities are not conserved? The charge is always conserved. The energy is always conserved. Momentum is always conserved. Rest mass is not conserved. What is the meaning of a term rest mass? Rest mass means the mass, because when the particles are moving at a slower speed or they are stationary, let's say the electron has a mass of 9.11 into 10 to the power minus 31 kg. But when this electron, the same electron move close to speed of a light, like let's say it move at 0.9 c. So close to c is the speed of light. So when it start to move close to speed of light, the mass does not remain constant, the mass start to increase. it won't be 9.11 exponent minus 31 kg. It will be greater than this value, the mass of electron. So the rest mass is not conserved because in a particle accelerator, as the particles start to move close to speed of a light, so as a result, the mass increases, so the mass is not conserved. So even if we move close to speed of a light, our mass will also change. Is it clear? So this is called relativistic effect. What is a relativistic effect? When we travel close to speed of a light, the mass will increase, the time and the length will become shorter. Like the length, say you're traveling at a speed of a light, the same 1 kilometer won't be 1 kilometer, it will be shorter. And same thing, the time dilation. So the time will also say the same 1 minute will not be same 1 minute for you. Like on Earth, what was 1 minute, that same will not be there for you. It will be much longer. So time dilate, mass increases, and the length contract. Which row of the table shows a possible arrangement of a quark in a baryon and a meson? So baryon means a baryon is a combination of three quarks, okay? But it should be either all of them should be quark or all of them should be anti-quark when it's a baryon. So this cannot be an answer. Why this cannot be an answer? Because one of them is anti-quark. This is also not an answer. One of them is quark. So either this can be an answer or the B or C. But when we check a meson, meson is a combination of either a quark and anti-quark. But not identical anti-quark. That means the quark and anti-quark should be there. So when we check, this is a combination of two quarks. This is a combination of quark and anti-quark. That's why C will be the right answer. In question 4D, the diagram shows a track from an event at P in a bubble chamber. Like we have different particle track detectors. So bubble chamber is one of them. There's a uniform magnetic field which is into. So if a magnetic field is into, like pointing into, it produces two particles. You can clearly see the curvature of the track give us the idea of the momentum, because this is having a large curvature, so it is having a greater momentum. This is having a smaller curvature, so it is having a smaller like it bend more, so less curve, it means it is having a smaller momentum. And the direction are opposite. As you can see, their directions are opposite. So if the directions are opposite, if one is a positive particle, another one will be a negative particle. And which we can also identify which one is a positive, which one is negative. If we apply the left hand rule for this track, the direction of the force is in this way. Our index finger is pointing into. So the diagram shows a track from an event at P in a bubble chamber. There's a uniform magnetic field which is into. So magnetic field is pointing into. So as this magnetic field is pointing into, and when I apply the direction, which one is positive, which one is negative. So when we apply this direction, so index finger is pointing into for this track. The thumb is pointing, thumb should point towards the force. So my thumb is pointing towards the force, which is this way. This is the index. Index finger is pointing the magnetic field, thumb is pointing the force, and this is particle direction. So means this shows that this will be a positive particle, so this will be a negative particle. Because index finger represent the magnetic field, which they mentioned it is into. So the index finger is pointing into. Thumb is the direction of the force. So the direction of the force is in this way. So where the second finger is pointing is the direction of the particle. So means this will be the positive particle as it follow the rule. How do we know which hand we have to use? Like we use a left hand first. If it matches with our result, we'll say this is the positive particle. Otherwise, it will be opposite. Like if it was a negative particle, as you can see. So when I apply a rule here, The two particles are going out, when I apply the rule, magnetic field dimension, it is into. So magnetic field is into, I'm applying a left hand on any one of them you can apply. So if I am applying a left hand on this left hand particle, so the force is pointing in this way. This is the direction of the motion of the particle, and thumb is pointing in, if index finger is pointing into. So this particle is following a left hand. But if I try to apply a left hand for the second particle, so the force is towards the center, but when I try to apply for this particle, the force is in this direction according to the left hand. So means this is not the positive particle, this is a negative particle. It won't follow the rule. The negative will be opposite. So which of the following is a reason why the track shown cannot represent the production of proton and antiproton with an equal kinetic energy? If they were having an equal kinetic energy, then what should be the track? They should have equal curvature. The curvature of the track should be same. So the curvature is perpendicular to magnetic field. No, that is not showing an idea. The track curves are different direction. Yeah, the track curve should be different direction when they're particle and antiparticle. If there's a proton and antiproton, they should have a different direction tracks. The track have different curvature. So as you can see here, because the tracks have different curvature, so that's why if it was a proton and antiproton, the track should have equal curvature if they have the same kinetic energy. If the two particles having different kinetic energies, then the track will be different curvatures. So the curvature of the track shows their kinetic energy or the momentum. They have the same kinetic energies or same momentum. It means the track should have same curvature. If they are opposite charged particles, then the direction will be different. And there is no track before point P, that if it was a proton and antiproton, like particle and antiparticle is produced, so definitely the total charge should be conserved. So initially, if it's a neutral particle, the neutral particle does not give us any track. Like there is no track for the neutron. Why neutron does not give any track? Because it's a neutral particle, so it does not cause any ionization. So the tracks have a different curvature. That's why it cannot show the proton and antiproton with the same kinetic energy. Is it clear? So this is about the particle physics and accelerated. More we will do in the next session.